Okay, so last time we talked about power functions. We learned about the end behavior of power functions. We defined a polynomial. We practiced identifying polynomials. And we learned that polynomial end behavior follows the end behavior of the leading term, whatever the term with the highest exponent looks like. Okay? Today we're going to talk, instead about end behavior, we're going to talk about local behavior. Ooh. What does local behavior mean? Close to what? Local behavior is the middle of the graph. Yeah. End behavior is the far edges. Local behavior is the middle, near the origin. In and around the origin. Yeah. So it's the region of the graph that has the origin in the middle. And you could like zoom in really close if your function is small. If your function's big, you might want to zoom out a little bit. But the origin should be in the picture somewhere. We're not at infinity is the big part. So near the origin is where all those other terms, the lower order terms, start coming into play. And there are three things that we are looking for in terms of the middle behavior or local behavior of a polynomial. We're looking for turning points, which are where the curve changes direction. We're looking for x-intercepts and y-intercepts. So let's go through them and then we're going to practice finding them. Yeah. So turning points occur where the function changes from increasing to decreasing, or vice versa. So it changes from going up to going down, or it changes from going down to going up. Yeah, those are called turning points. We have seen them before when we talked about what graphs look like. We called these guys local mins or maxes, also known as local extrema. And we practiced finding these on our calculator. We learned that after we graphed a function on our calculator, we could press second trace. And one of the options was minimum. Pardon me while I choke on my lunch here. And one of them was maximum. And you'd estimate a lower bound and an upper bound, and then your calculator would guess. Yeah. We know for a polynomial of degree n, I should have at most n minus 1 turning points. I might have fewer than that. I will never have more than that. For example, if I am a quadratic, what shape graph does a quadratic make? Y equals x squared. What shape is that? Yeah, I see Aubrey making this with her fingers. Good, it's the U shape. Yeah, it's the parabola. That's a degree 2 polynomial. How many turning points are in that graph? How many times does it change direction from increasing to decreasing? 1. Yeah, 1. There's one vertex at the bottom or the top, depending on whether it's a happy face or a frowny face, which is 2 minus 1. So that check out, that matches that pattern. So all polynomials should match that pattern. The maximum number of turning points or bumps that they can have in their graph is 1 degree less than the polynomial degree. Next thing we look for are y-intercepts. Y-intercepts are where the graph crosses the y-axis, which is where x is 0. And these occur at the point 0, comma, a sub 0. That is notation that we saw last week. if you look where we defined a polynomial, I'm going to go back a page. I'm pretty sure it's here. Where we defined a polynomial here on that second page, you'll notice that the last term of the polynomial is a sub 0. You'll notice that the labelings on those a's are our coefficients, match the exponents on the ends that are next to them, yeah? A sub n goes with x n, a2 goes with x squared, a1 goes with x to the first, a0 technically goes with x to the 0. But x to the 0 is just 1, and so we drop it. This term is also called our constant term. The constant term is our y-intercept. If I set all of the x's to 0, that's the only thing that's going to be left. So when x is 0, y is equal to that constant term. So a sub 0 is the constant term of the polynomial. Polynomials only have one constant term, therefore I should only have one y-intercept. I also know I should only have one y-intercept because if I had two, I would fail the vertical line test, which means I wouldn't be a function. Sad face. Last one. X-intercepts occur where y is 0. Yeah. And we call these sometimes the zeros of the function. These are the solutions to the equation f of x equals 0. And we can find them a couple of ways. The most common way is by factoring. That was the first way you learned to solve quadratics back in Math 2. If I can factor my polynomial, I know that I set each of the factors equal to 0 and solve them separately. There are some other methods. If I can't factor a quadratic, what else can I do with it? How else do you solve quadratic equations other than factoring? Oh, frowny face. I don't think any of you were in my Math 2 class, were you? Alex was. He should know, because this is the one thing I told you to remember from Math 2. You had to remember one thing. Sad face, the quadratic equation. Minus b plus or minus square root b squared minus 4c all over 2a. Your teachers didn't make you sing Pop Goes the Weasel with that? Frowny face. So there are, for some polynomials, other ways other than factoring that we can get at the solution. Over the next 2 weeks or so, we're going to look at some of those other ways for higher order polynomials beyond an x squared. For x squareds, factoring and quadratic method. Yeah. If I am looking at a polynomial of degree n, I will have at most n x-intercepts. Meaning if my polynomial is degree 5, I will have at most 5 x-intercepts. If I have polynomial degree 100, I will have at most 100 x-intercepts. Notice it says at most. If I draw a quadratic that looks like this, how many x-intercepts do I have? 1, just the vertex. And it's a repeated intercept. It's a repeated factor. That guy shows up twice. I'd have x plus 2 times x plus 2. Yeah. It's also possible I could have a quadratic that looked like this. How many x-intercepts does that guy have? 0. Yeah. The roots of the polynomial should always be n roots. Some of them will not be real solutions. And the ones that are not real don't show up in the graph as intercepts. So we can have two things happen. We can have a real root that gets duplicated, we can have a non-real root. Looks like that. Yeah, we're going to talk about that over the next couple of weeks. It's fun. It's a review of math too. We're going to practice. We're going to do some together. I'm going to have you try one or two on your own. Yeah, and then we'll be done with 3a. So first example says, for the polynomial function shown below, determine the x and y intercepts. Determine the x and y intercepts. So I'm just doing the last two boxes, x and y intercepts. I'm going to start with y-intercepts first because they're usually pretty easy. Whoops. So how do I find my y-intercept? Y-intercept happens when what is true? You wrote it down in your box. Ethan, when does that x or y-intercept happen? When x equals what? X equals 0, yeah. So I'm going to take my function and I'm going to plug in x is 0. 0 minus 2, 0 plus 1, 0 minus 4. How did you do it?
I just take all
the x's? And that works because zeros drop out anyway. Yeah. -2 times 1 times -4 is positive 8, assuming I can do that in my head correctly. I don't see anyone making frowny faces at me. I'm going to assume I did that correctly. Yes, Bruno? Doesn't matter. With multiplication, the order that you do it in doesn't matter. That's okay. Next one, we do the x-intercepts, which are when f of x is equal to 0, meaning that whole expression is equal to 0. And we learned something in Math 2 called the zero product property, which tells me if I'm multiplying a bunch of stuff together and my answer is 0, one of the things in that string of multiplication must have been 0. That's the only way I can get 0 as an answer when I multiply. I had to multiply by 0. So I know one of these three polynomials must be 0. And that is an easier problem because that's 3 separate linear equations. We know how to do those. Want to solve x minus 2 equals 0, I add 2 to both sides. I get x is equal to 2. If I solve x plus 1 equals 0, I have to subtract 1 from both sides, so I get x is -1. Last one, I add 4 to both sides, I get x equals 4. And again, I don't hear any groaning and I don't see any frowny faces, so I'm assuming I did that correctly. Alex is nodding. I now have a lot of information about my graph. What's the degree of this function? How many x's are in that original expression? 3, yeah. My degree is equal to 3. There aren't any negatives in front of those x's, so my leading term is just going to be x cubed. It's positive and odd. So I have a sneaking suspicion that my graph probably looks like this, and I know where those 3 intercepts now are. -1, +2, +4. We're going to check by graphing it on our calculator, which is why I asked you to get these out earlier. So y equals, and you're going to type the expression on the right exactly as it's written on the page. The button next to the green alpha button. Well, let's take a look. What does yours look like? So go zoom, and then select option 6, Z standard. Recenter your graph.
Oh, there it is.
Yeah. When in doubt, zoom standard. When it gives you that error option, select go to next time, and it'll show you what the boo-boo is. No calculator? Does it work when it's plugged in? Okay, I'm gonna go get you a charger. If it works as long as it's plugged in, just bring your charger with you. Yeah. Everybody should have that familiar S shape that we get with cubics on their graph. You should be seeing a y-intercept of 8. That peak should be pretty high up. You're welcome. We should be seeing 3 x-intercepts. Is there anybody who's not getting that? Nope, it looks like everybody's got it. Very good. And remember that we talked about turning points. We know because this is a degree 3 polynomial, what's the maximum number of turning points I can have? It's 2, n minus 1. And notice this graph has 2. It has a local max here. It has a local min here. And we practiced how to find those with our calculator like last week. Yeah. Good. Very good. I'm going to do one more with you, and then I'm going to have you try one. Next one says f of x equals x to the 4th minus 4x squared minus 45. We haven't, but we can. What is the y-intercept, Bruno? It is negative 45. Very good. If it's in standard or general form, it's just the constant term. Good. The trade-off. The x-intercept is less direct. Same process. I take my expression and I set it equal to 0. And I look for factoring patterns. That kind of looks like a quadratic, except the exponents are double what they should be. A 4 instead of a 2. I have a 2 instead of a 1. I'm going to rewrite this as x squared minus 4x squared minus 45. Instead of treating x as my variable, I'm treating x squared as my variable. We could rewrite this if that makes you uncomfortable. We could write y equals x squared and rewrite this as y squared minus 4y minus 45 equals 0. Both of those would do the same thing. I want to factor that guy. So I'm looking for numbers that multiply to negative 45 and add to negative 4. Somebody have a suggestion? Yes, Bruno.
I should think of negative 9 and 5.
Negative 9 and 5. If we add negative 9 and 5, do we get negative 4? I see some nodding. I think Bruno hit the nail on the head. Very good. So this is y minus 9 times y plus 5. And remember that y was x squared. I don't expect you remember this trick. You would have seen it in math too, but it's been a long time. Yeah. From here, it's just like the last one. Now that it's factored, set each factor equal to 0. So I can have x squared minus 9 equals 0, or x squared plus 5 equals 0. For the x squared minus 9 equals 0, what's the first thing I should do if I want to solve for x? Add 9, perfect. So x squared equals 9. I don't want x squared, I want x. I hear the mumbling. Square root, yeah. I agree. So x equals, and I know that when I take the square root of a number, 2 answers. Plus 3 or minus 3. I also know that because x squared minus 9 is a difference of squares. It factors into x plus 3, x minus 3. I should get 2 roots. Perfect. I'm going to use that same set of step lists on the other equation. I have to subtract 5 from both sides. I have to take a square root. Am I allowed to take square roots of negatives? No. So these guys here are non-real roots of the polynomial. They don't show up in the graph. They exist, but not in the graph. Correct. So even though this is a 4th degree polynomial, he only has 2 x-intercepts, positive 3 and negative 3. And he's got a y-intercept way down at negative 45. I have a sneaking suspicion since he's only got 2 intercepts, he's going to look vaguely like a quadratic. What I'd like to challenge you to do is I'd like to challenge you to graph it on your graphing calculator. Let's take a look at what this guy looks like. It's good for you. What does he look like? Graphing. Before you do C, graph B. Graph B. We want to see what B looks like. Graph B. We want to check, make sure we did our work correctly. Yes.
What should we put on the y?
Oh, so we're going to go x, and then to get a 4th power, we use the caret button, and then 4, and then sideways to get out of the exponent. And then, yeah.
Oh, just put like this.
Just the original equation.
Okay.
I don't know. I don't know what your graph looks like. Yes, if you're set to zoom standard, that's exactly what it'll look like. Because where is the y-intercept?
Oh, yeah, 45.
Way down at 45.
Yeah,
It's off the graph. Good. That's what you should see.
Can you do zoom, like, adjust or something?
There's zoom fit.
Yeah, zoom fit.
You could do zoom fit, yeah. And I see Jackie got the same thing Bruno got. Juliet is still working on it. Have you graphed it yet? No.
I don't see that.
Just make sure we know how to graph. That's why some of why we're practicing. Oh, the red one is the new one.
Yeah.
Perfect. That's okay. As long as you know which color is which. Yeah, perfect. I'm seeing a whole lot of graphs on calculators that look like this, and they don't show the bottom because the bottom is way down at negative 45. Yeah. So our graph is doing this, and it's really flat down at the bottom, and then it comes back up pretty sharply. We know those are at negative 3 and positive 3. We know this is down at negative 45. Yeah. Notice, really only one turning point there. We go from decreasing to increasing. This is a fourth power polynomial with only one turning point. So it is okay that you have less than n minus 1. You should never have more than n minus 1. Okay, I'm going to put a couple minutes on the clock. There is one more below this, number C. I'd like you to try C in your small group. I'm going to call on some people to come up and do that for us. Biggest exponent. Biggest exponent. Well, if we don't finish, we can finish tomorrow.
I don't think we're going to finish because the voting is in seconds.
I think you overestimate the accuracy of our bell system, Bruno.
2, 1.
All right, guys. We'll pick up where we left off yesterday. This will be our warm-up tomorrow. We're going to continue with 3b and polynomial long division tomorrow. Yay. Thank you, Ellie.